Hey guys, how's it going? This is Siri and I'm back with another PyTorch video, and in this video we're going to be talking about what accumulating grad functions are. Okay, gradient functions are. Okay, and in our last video we've talked about the gradient descent algorithm and how we implement it, and we've talked about we talked about AutoGrad in our last video and PyTorch's automatic differentiation engine. Okay, so what we've been doing in the past, like many videos, is we've been talking about this whole machine learning process. Okay, and I would definitely recommend going back to those first few videos, about this learning process, about what parameters mean, about what updating parameters mean, about how we start off with some data and, need to choose a mathematical model that you think will best represent the data. So y equals mx plus b best represents a line, and things like that, and starting off with some initial values for our parameters, which in this case are our weight and bias, or in other words, our slope and y-intercept, and how this is an iterative process to update your parameters to get the best values for them to actually make that line represent your data. So we need the best values for our slope and our y-intercept, because we can't have a line that's y equals 4x plus 7, when in reality our data can be modeled by the equation y equals 2x plus 1 or something. Okay, and we've talked about how loss functions help us do that, and it's a function that we want to minimize, and there are a couple of different ways which we can, calculate that loss, which are the absolute value and the square of the difference between the predicted and the actual value. We're using the second one. We went through the model definition, loss definition, and these are really the most basic things you can do. This is just a regular Python function. We're not using any of the, the neural network tools that PyTorch gives us and provides for us just yet, because we want to be focusing on the, the mechanical aspect and what's actually going on. We don't want to jump into that non-linear component just yet without fully understanding what is going on, what is the computer doing, and how is it able to, associate this input with this particular output. Okay, and we learned how to change /update /estimate W and B so that our loss reaches a minimum. Okay, we used a number guessing game. We talked about gradient descent, which was to compute the rate of change of the loss with respect to each parameter. And we're going to be modifying each parameter by a small delta x in the direction of the decreasing loss. And so we found a way to automate that. Okay, but first of all, we have a learning rate and we're scaling that rate of change of loss with respect to each of our parameters, W and B. We're scaling that by a really small number because we don't want to update the parameters too quickly. So we have a learning rate, and that's our hyperparameter that we can adjust. And and it's an extremely important hyperparameter. And we've normalized the inputs so that we don't get crazy values for, our loss. And we found out how to implement that, and we've also talked about how AutoGrad helps us do that automatically without having to define a derivative for each of the million or couple of million, or I don't know, around that range. We don't need to define derivatives for each one of those because that's going to be a pain in the neck. And we can use PyTorch's automatic differentiation engine. Other deep learning frameworks have this differentiation engine too. PyTorch's one is called AutoGrad, automatic gradient. Okay. We have two different passes, forward pass, backward pass. We talked about the computational graph, and how that helps us visualize how tensors are being modified throughout these updates, these iterative updates. and so how that's being done at only the leaf nodes, not the other, parts of the computation that you take to get there, to get to the updated version. So it's where the computation begins, and the you create new tensors along the way, and the intermediate steps. Whoa, didn't mean. Okay, yeah, and so there are a bunch of intermediate steps, and we don't track the derivatives for that. And by the way, gradient is just a vector of derivatives. Okay, and yeah, and so we've redefined, actually we just copy pasted the model definition and the loss function definition, and we set parameters.grad. We confirmed that params.grad, which is an attribute of our parameters, we've confirmed that it's true. We've confirmed that it doesn't have any gradients stored in it yet. So, okay, this is kind of an important point. So, if we have tensors, right, and if we pass it through a model, we get computed gradients from that. So, when we passed in, we're getting the gradient, right? We're getting the vector of derivatives. And if you're kind of confused as to how derivatives even play a role in this whole machine learning process, I would definitely recommend, watching this whole backpropagation video, and about, this chain rule and how we compute the loss. And how we update the parameters. Yeah, that's the video. How we update the parameters based on the loss function. So definitely watch the video on how we change /update /estimate W and B so that our loss reaches a minimum. Okay, so what we're going to be talking about right now is that when we have the grad attribute of params that stores the updated or calculated gradient, how that relates to the gradient we get in the next iteration, and what things we need to look out for and watch out for so that we don't get wrong results. And okay, so this video is going to be about accumulating grad functions. Okay, and grad is just gradient. Okay. So, we've learned how we can call backward, okay, on the loss to make a backward pass, go through the computation graph, see how this updated parameter came to be, and what steps the original tensor took to get there. And that's important to us because we need to know how the derivatives, the gradient and the derivatives were calculated so that we can update the parameters for the next iteration. So we're on the current iteration, we're looking at how we came from the previous iteration to the current iteration so that we can make our updates for the next iteration. Okay, so hopefully that's clear. And, we're calling backward on loss so that we can go through that backward pass. And we've talked about forward and backward passes in our last video, in our, our AutoGrad video. And we talked about where that falls on our computational graph and what that graph even is. So if you're confused, definitely go back to this video. Okay, so yeah, we call the backward pass, we do the chain rule, and we have our new updated parameters. Okay, but we want to call backward a second time, right? We call backward, first of all, our backward's going to be in the loop, right? So we're going to be calling backward multiple times. So we get, the gradients for each of the different iterations. Now, what's the problem with doing that without catching that little sneaky thing that's going to make everything go wrong? Well, first of all, you already called backward on the loss in your iteration. And your grad attribute for each of the different parameters, okay, for each of the different params, is already populated. So your grad attribute is already populated with these values, and you are calling backward a second time, or the third time, or however many, whatever iteration you're on, those many times, right? And the problem is that the gradients for the previous iteration were not erased yet. And so, for example, if we're on the second iteration, okay, let's start at the beginning. We're on the first iteration, we call backward, and now our params' grad attribute is populated with 4,517.2969 and 82.6000. Okay, so this is probably for the weight, and this is for the bias. The loss, the derivative of the loss with respect to that. Okay, so now we're on the second iteration. This is over. Okay, we already did the first iteration. Now we're on the second iteration. Okay, params.grad is still equal to that. Now when you call backward again, we compute new gradients. And those new gradients don't stand by itself. It's not like, oh, we do the first iteration, now this is params.grad, and we do the second iteration, now we have new params.grad based on the updated parameters. What actually happens is that those get added to the previous iteration's grad values. So, if this was the gradient for the first iteration, and I'm not really sure, I'm just making up numbers here. Maybe since you're finding the slope, maybe, I don't know, maybe it's 401 and whatever. Just making up numbers here, don't take this, at face value. And so we have, maybe 121 point whatever. Okay, so this is from the first iteration, this is from the second. And what actually happens is that this isn't what gets populated into params.grad. What actually gets populated is this, okay, the one that we got, plus this. Okay, so we're literally adding them. Okay, so we can, okay, 1 second. Okay, so it's going to be this. The weight gradient, the weight derivative is going to be added to this, the previous one. And the second one is going to be added to the previous one we got for the bias. So you see this idea of accumulating these values, okay? Because we're not just, saying, oh, this is 4,401, this is 121.24, those are the values in the gradient for iteration 2. We are actually adding it to the previous values that were stored in params.grad, okay? And we don't want that, right? We just want the derivatives that were based on the updated values. And this addition is not it, okay? This is the wrong gradient, and you don't want this to happen, okay? You do not want this accumulating of derivatives, which is just adding the new gradient to the one AutoGrad computed from the previous iteration. Okay? Because this is wrong. This is the wrong derivative. This isn't even first of all, this is wrong, But this wasn't the first one. This is the first one plus the second one, and that's not right. Because, because it's giving your model, it's giving your model the wrong values to base its next update on. Okay, so if this is the derivatives, if these are the derivatives that you give and pass on to the next iteration, so onto the third iteration, this is completely wrong, right? So instead of getting closer to the representation that you want, instead of getting closer to whatever the 4x plus 7 you want to model your input and output, you're going even further away from. So maybe maybe the slope was negative, and it's getting even more negative when it should in fact be positive. So it's giving your model the wrong values to base its next update on. So this is not good. Okay, so what do we need to do? We need to make the derivatives 0 after each iteration. So once it's computed the value, and once it knows, hey, this is what I'm going to be basing my next update on, the following update does not need to be the sum, but rather the new update that we get it, from, if that makes sense. So, you get this idea that you don't want the sum, you just want the regular value that it computed. So that's all that matters. And what also matters is that we need to make the grad attribute equal to 0 at the end of each iteration, so that this accumulating doesn't happen. Okay? Okay, so it's going to be adding the gradients of one iteration to those of the previous iterations, which gets you the wrong gradient. Okay, so we don't want that, like we said. And so if params.grad is not none, so if it's populated with some values, then what we want is that we want to say params.grad 0. So if you remember, okay, that's not it. Params.grad is, a tensor, and we're calling .0 and underscore. If you recall what this underscore does, it means we're doing an in-place operation, so we are actually modifying these tensors. We're not just returning a new value that looks like this. We're actually modifying params.grad. So this is what needs to go into our training loop. So let's literally just copy paste our training loop and make it better, so that we're not adding the gradients to the previous gradients of the previous iterations. So where was it defined? Here. Okay. And this is some interesting code that's worth diving deeper into, and we've done that in our previous videos. But this is just some chain rule that's going on behind the scenes, the way the loss function is defined. But this is the predicted value, the loss, the gradients, and now the updated parameters. So let's say if params, oh yikes, if params is not none, okay, params.grad.0, Okay, and it might look like I'm doing this at the beginning of the iteration, but it's actually at the end of the previous iteration. So this, for the first time it runs, params grad is going to be none, so this isn't going to execute because it's already going to be 0. And so we do our stuff, we have some new parameters, okay, we updated them. And so now we go back, and so now our params.grad is populated. Okay, after we print it out, our params.grad is populated, so now when we run this again, this is not none, and we set params.grad equal to 0 by calling this method on it. Okay, and so when we call the backward method, we are actually going to do something interesting with this line, and we're going to put it within a with block. Okay, so with torch.noGrad. So under these circumstances, what we want to do is, params, we want to do the updating. So we do this because we don't actually want to calculate the gradients for this updating part, because it's going to get confused on which, our model is going to get confused, and PyTorch is going to get confused on which parameter we're actually computing the gradient on, because we're updating it at the same time. And so we don't want any additional edges or like connections or like operations being added to our computation graph, okay, because it's not necessary. And when we call backward, we're done with the forward pass, and then we go back, and all that information gets cleared because now we have the values at the leaf nodes, which are, the weight and the bias, which is where all our computation began and was based off of. So that's the only thing that matters to us, and that's the only thing that stays stored in memory, because it's a waste of memory to keep track of all the gradients for all the unnecessary parts once we're done with that backward pass. Okay. And so yeah, let's run this. Cool. And let's call it training loop. Okay, n epochs. Okay, actually, this, we don't want to print everything. Okay, let's make this really big. And first of all, I don't want to print everything actually here. So let's just print out this. We don't need to print out all the parameters in the gradient, because if I make the number of epochs really big, then it's going to be kind of crazy. So if the epoch is divisible by 500, assuming that our epochs are going to be much larger, the number of epochs are going to be much larger than that, set it equal to 0. Then we're going to print it. Okay, so let's run this again, and training loop, and epochs. Okay, because this is an epochs for every epoch in the epochs, we're doing all this. So let's set n epochs equal to 5,000. Okay. And let's say the learning rate is equal to 1e2 params. It's going to be initialized to 0 and 1, or actually 1 and 0 for weight and bias respectively. So the slope is going to be 1, the bias is going to be 0. Torch.tensor parentheses 1.0 0.0, and we're going to set requires grad equal to true. And remember, we do this because if this is not true for the leaf nodes and from where you start the computation, no matter how many computations you take to get to the next tensor, the next updated parameters tensor, by the time you get there, it's not going to be calculating anything because the original tensor was set to requires grad equals false. So that's why we set requires grad equal to true, so that we can track it for all of the parameters that we need in order to get to the output tensor, which has the updated parameters. So yeah. And TU, temperature unknown. And if you weren't following along with the example, don't worry, this is just like the input, and this is going to be the output. And we're going to be setting it equal to the normalized version. So U is unknown, just part of the example problem, and N means normalized. So when we run that, okay, torch is not defined. Okay. Okay, I guess all of our stuff is not defined yet. So let's run this. Okay, we ran this. Oh no, never mind. Okay, this should be a markdown. Okay, great. So now we have like 500, 1,000, 1,500, 2,000, 2,500, 3,000, 3,500, etc. until 5,000. So our loss is getting really small, and now we're not like accumulating any of our gradients. Okay. Yeah, I think that's pretty much it for this video. Hopefully you got the idea of what accumulating gradient functions are, and how that's not good, that's not what we want, and we have a solution for that by setting this equal to 0, or like populating it with 0 at the end of each iteration, or at the beginning of every new iteration if it's not equal to none. And yeah, so that's our solution, and we also don't want to update it we also don't want to calculate the gradient during the updating part. To calculate gradient during updating part. Okay, so yeah, hopefully you learned something new today, and I'm looking forward to seeing you guys in my next video, where we're going to be talking about the different optimizers and different optimizer objects that we can create. And so you can look forward to that for next time. But for now, I hope you learned something new, and don't forget to like, comment, and subscribe.